Did you know that our night sky is adorned with over 100 billion stars just in our galaxy alone? Each of these twinkling marvels is more than just a beautiful spectacle. They are powerhouses, colossal factories of light and heat, fueling life as we know it. Imagine each star as a grand fireplace, warming up the cosmic hearth. They shimmer and sparkle not just for our aesthetic delight, but as a testament to the energy they constantly generate. These celestial bodies, scattered across the cosmos, form the intricate tapestry of our universe. From the smallest red dwarf to the largest supergiant, each star plays a crucial role in the cosmic orchestra. Some are solitary performers, while others thrive in clusters, singing the symphony of the cosmos. So, as you gaze upon the night sky, remember that each glimmer is a story of cosmic energy and stellar life. Now, have you ever wondered about the life of these twinkling marvels? Stars like us go through a life cycle. They are born, live through an exciting journey, and then die. But how exactly is a star born? Well, our story begins in a nebula, a colossal sprawling cloud of dust and gas that stretches across the vast expanse of space. Nebulas are the cosmic nurseries of the universe, the places where stars begin their lives. They're composed largely of hydrogen, the most basic and abundant element in the universe, alongside a smattering of other elements like helium and trace amounts of heavier elements. Now, within these nebulae, something fascinating happens. The gas and dust start to clump together. The force behind this is none other than gravity, the cosmic glue that holds our universe together. Gravity pulls the particles of gas and dust towards each other, causing them to condense into a dense, hot core. This is the beginning of a protostar, the earliest stage of a star's life. As more and more material falls into this protostar, it grows in size and its temperature rises. The heart of the protostar becomes so hot that it ignites nuclear fusion, a process where hydrogen atoms combine to form helium. This process releases an enormous amount of energy, causing the protostar to shine brightly. But it's not a star just yet. It's going through its toddler stage, if you will. The protostar continues to accumulate mass from its surrounding nebula until it has gathered enough material. At this point, it has enough gravitational force to sustain nuclear fusion in its core. This is the moment when a protostar officially becomes a star. The energy created by fusion pushes outward, counteracting the force of gravity pulling inward. This equilibrium state or balance of forces is what defines a star. Congratulations, the birth of a star has just taken place. This newly born star, now all set to shine, will continue its journey through the cosmos, living out its life as a main sequence star. And just like that, a star begins its life. Once a star is born, it enters the prime of its life, known as the main sequence. During this vibrant and stable phase, our stellar actors undergo a process that lights up the universe. It's rather like the star's coming-of-age story where it starts to truly shine. Now imagine the star as a colossal cosmic kitchen. Within its fiery heart, the star begins to cook up something extraordinary. It fuses hydrogen atoms together to create helium. This is no ordinary culinary feat, however. This process, known as nuclear fusion, is what powers a star and enables it to shine so brightly. Just picture it. Inside the core of the star, intense heat and pressure force hydrogen atoms together. When they collide, they fuse, creating helium and releasing a tremendous amount of energy. This energy then travels out from the star's core, through its outer layers, and finally into the vast expanse of space. This energy that stars emit, we perceive it as light and heat. It's the warm glow of the sun on your face on a summer day, the twinkling of distant stars in the night sky, the mesmerizing dance of the northern lights. All of these are possible because of the energy produced by stars during their main sequence phase. But just how long does this phase last? Well, it depends on the star. Larger stars burn through their hydrogen supply faster, and so their main sequence phase is shorter. For smaller stars like our Sun, this phase can last for billions of years. Remember, the more massive a star is, the shorter its life. A star 20 times the mass of our Sun might shine brightly for only 10 million years. In contrast, a star half the size of our Sun might continue to shine for more than 100 billion years. This stable period of a star's life, the main sequence, can last for billions of years. So, next time you gaze up at the night sky, remember, You're witnessing stars in the prime of their celestial lives, cooking up a stellar light show, one fusion reaction at a time. As stars exhaust their hydrogen supplies, they start to age and enter the next phase of their life cycle. This stage is a testament to the resilience and adaptability of these celestial bodies, a phenomenon that is truly awe-inspiring. Imagine a star. It's been burning hydrogen in its core for billions of years, steadily releasing energy and shining brightly. But nothing lasts forever, and as the hydrogen supply dwindles, the star begins to change. It starts to burn helium, a heavier element in its core. This shift causes the star to expand dramatically, transforming into what we call a red giant. It's a star in its twilight years, bloated and glowing a deep, rich red. But why does it turn red, you ask? Well, as the star expands, its surface temperature drops. And with this drop in temperature, the light it emits shifts to the red end of the spectrum, hence the name red giant. It's a bit like a celestial retirement, the star swelling in size and glowing a warm, comforting red. However, this stage, too, is temporary. Eventually, the helium fuel in the core runs out, and the star can't maintain its expanded size. Gravity starts to take over, pulling the outer layers of the star inward. The star contracts, shrinking in size dramatically. What's left is a hot, dense core, a white dwarf. Don't be fooled by the name, though. White dwarfs are anything but dull. These stellar remnants are incredibly dense, packing the mass of our sun into a sphere roughly the size of Earth. They glow with a fierce, white heat, the last vestiges of their former energy. But even this stage isn't the end. White dwarfs can continue to evolve, their fates shaped by their mass and the cosmic environment around them. Some will cool and fade slowly over billions of years, while others might meet a more dramatic end. This is how stars age, transforming from red giants to white dwarfs. It's a cosmic dance of expansion and contraction, a testament to the ever-changing nature of our universe. The final stages of a star's life are dramatic and spectacular, leading to its ultimate demise. As the star exhausts its nuclear fuel, it undergoes extreme transformations. The fate of a star depends largely on its mass. The heavyweight stars, those with masses several times greater than our Sun, meet an explosive end. As the star's core collapses, it triggers a supernova explosion. This is not your average fireworks show. It is an event so powerful that, for a short while, a single supernova can outshine an entire galaxy. The explosion disperses the outer layers of the star across space, seeding the universe with elements heavier than iron, like gold and uranium. These are the very elements that make up the planets, and indeed life itself. Quite a legacy for a star, wouldn't you say? But what of the star's core, the epicenter of the explosion? Well, if the core is massive enough, it continues to collapse under its own gravity. This collapse is so extreme that it forms a black hole, a region of space where gravity is so strong that not even light can escape its grasp. These cosmic phenomena are truly the stuff of science fiction. Invisible to the naked eye, we can only detect black holes by their effects on nearby objects. On the other hand, stars with masses similar to our Sun meet a less dramatic but equally fascinating end. Once they exhaust their nuclear fuel, they shed their outer layers and leave behind a dense core, a white dwarf. Over billions of years, these white dwarfs cool and fade, eventually becoming black dwarfs. These remnants of stars are so faint, they're extremely difficult to detect. And so a star meets its end either in a brilliant explosion or by vanishing into the darkness. But remember, the story doesn't end here. The death of a star sets the stage for the birth of new stars, continuing the cosmic cycle of life and death. The end of a star, however, is not the end of the story. As a star meets its dramatic end, it sets the stage for the birth of new stars. A supernova, the explosive death of a star, is a cataclysmic event that can outshine entire galaxies. But from this celestial pyrotechnics, a nebula is born. This nebula, a vast cloud of dust and gas, is the celestial cradle where new stars come to life. The heavy elements forged in the heart of the dying star are now scattered across the cosmos, becoming the building blocks of future stars. This process of death and rebirth is the natural cycle of stellar evolution, a cycle that has been ongoing for billions of years. As one star dies, another is born, keeping the universe alive and glowing. It's a beautiful cosmic ballet, choreographed by the laws of physics, reminding us that even in death, there is creation.